Hey everybody, it's Mr. N here, and today we are going to talk about implicit differentiation. All right, what the heck is implicit differentiation? Well, let's first start with what we know. Everything that we've been doing so far has been explicit differentiation. So I have over here y as a function of x. Okay, so what does that mean? That means I have y equals, say, 2x to the fourth power. Y prime, you can take this derivative, and you would get 8x to the third power. That's explicit differentiation, where you've got y on one side, which is your f of x, and the other side of the equation is all in terms of x. Okay, so you've been able to differentiate those. Now, there are going to be situations, though, where what if it's not in terms of x? Well, we could take we don't have to take the derivative with respect to x. As you know, we could take the derivative with respect to y. We could take the derivative with respect to z, t, whatever. It just matters on the variable. But the key is, so you would have to get that term all by itself. So if I had s of t, okay, I'd have everything here with t's, all just t's on this side. But what if I could not separate that variable I'm trying to differentiate explicitly? And what do I mean by that? Well, let's take a look at this. Suppose I had this equation. Let's go ahead and highlight this. And this is x squared plus y squared equals 4. Well, what is this? Okay, if I graph this, we know it as a circle with a radius of 2. So I can go 2 in each direction. I would go ahead and graph my circle. And okay, there we go. And that's not such a nice circle, but we can deal with it. And basically what I'm trying to say is, okay, find the tangent line at a certain point. Right? That's what I want you to do. Find the tangent line at a certain point. All right, so to find the tangent line, we need to solve for y, and I take this equation right here, and I will go ahead and solve this for y, and I get y squared equals 4 minus x squared. All right, wait a minute. So that means y equals plus or minus the square root of 4 minus x squared. How do I, wait, so I have two equations here that I have to deal with, the positive and the negative. So that would mean I've got the top half of the circle. Let's go ahead and do that like this. I'll do two axes here. I've got the top half of the circle at a radius of 2, and the bottom half of the circle at a radius of 2. My circles don't look so great today. Right there. And I would have to do each one of these separately. Okay, but again, what if we don't have a situation where I can solve for y? What if it's impossible to solve for y? Like in cases like these, we don't always have to solve for y. Instead, we use this other method called implicit differentiation. So when do we use implicit differentiation? Pretty much whenever we can't solve for the variable we're looking to solve for. In other words, if I can't solve for y, I'm going to have to use implicit differentiation. If I'm trying to solve for z and I can't isolate z and put it by itself, I'm going to have to use implicit differentiation. Otherwise, if you can solve for the variable, do that and use explicit. Okay? Explicit is what we have been doing right here. Implicit is when I can't solve for a particular variable. In this case, I could solve for y, but then I had two separate cases. I had two different cases I had to examine. So instead of having two different cases, I can just go through and I can do this one with a method called implicit differentiation. And let's take a look at what we do and how we do implicit differentiation. First of all, implicit D, what we do is we will differentiate both sides of the equation with respect to x. So if I want to find dy dx of this, I would take the derivative with respect to x of this side and the derivative with respect to x of that side. Okay, so that means if I say derivative with respect to x of this equation, derivative with respect to x of that equation, well, this one, what's the derivative of a constant? That's going to be 0. Over here, the chain rule and your rules of differentiation allow you to distribute this. So I'm going to say the derivative with respect to x of x squared plus the derivative with respect to x of y squared. apply the chain rule as needed. Over here, let's see what happens, and I will break each of these down for you. First of all, suppose you had the derivative with respect to x of y squared. That's just this derivative, 2y dy dx. Notice I'm always going to put the derivative right after it. Over here, the derivative with respect to x squared is 2x. But no, look, I took the derivative of x with respect to x. What happens to this? It reduces out. Over here, the derivative of a constant is 0. Let me recap that again. I had this equation. Oops, I hate when this thing goes to the wrong item. I had this equation, x squared plus y squared equals 4. I took the derivative with respect to x of x squared. I took the derivative with respect to x, the derivative with respect to x of y squared equals, I took the derivative with respect to x of the 4. Okay, you're always taking the derivative with respect to x. Over here, this derivative becomes 2x. But I always multiply it by that differential. In this case, it was the derivative of x with respect to x. This reduces out like any other fraction to be 1. Over here, I get 2 times y, and I took the derivative of y with respect to x. We always have to keep this kind of sort of Leibniz notation. It's sort of our way of organizing it. Over here, I took the derivative of this with respect to x, but that's just 0. So now look at what I have left. I have 2x plus 2y dy dx equals 0. I can now isolate this dy dx, and that's my goal. So I'm going to subtract over, this is dx. I'm going to subtract over this guy, so that's 2x, and then I'm going to divide by 2y, and that'll give me negative 2x over positive 2y. These reduce out, so I'll have negative x over y as my solution. Okay, and that's what I did here, and that's what you see right here, and you can follow the work along here if you want. Just go ahead and pause it. Now let me note something. We often, again, I got to pick the right thing here. We often express dy dx as y prime. We don't use an x prime because this would just be dx over dx, which reduces out. So as a shortcut technique, we will often do the dy dx as y prime. Let's take a look at more examples here. We want to find the slope of the tangent of x squared plus y squared equals 4 at 1, negative 3. Now, what we would need to do here is we need to find a slope. And we would need to isolate y, but again, we've done this, we've talked about this, you get two outcomes, the positive and the negative. So instead of doing that, I'm going to go ahead and differentiate implicitly. And when I differentiate implicitly, this is the same exact problem that we just did, but we'll do it again anyway. I'm going to take the derivative of each of these with respect to x. So d dx of my x squared plus d dx of my y squared equals d dx of this 4, right? Really what I'm doing on the left side is d dx of this whole thing, but we can distribute that. Now, here is the other notation I'm going to show you. So this is what we're doing, but I'm going to do it a little bit different so that you understand the other notation. I take the derivative here, I get 2x. Now normally I would put x prime, but x prime is dx over dx, which is 1. So I don't put that x prime is what I'm going to try to tell you here. You don't do that. You only put a y prime whenever you differentiate, because y prime stands for dy over dx. So over here, remember when I took the derivative, I said this would be 2x, dx over dx, and that went away. This would be 2y dy over dx, but that stays. Well, instead of writing dy dx, I'm going to write y primes. So I take the derivative here, and I get 2y, y prime. I take the derivative there, I get 0. Again, just to kind of like make it a shortcut type thing, whenever you're taking a derivative with respect to that same variable, you don't put anything there because it cancels out. So in our case, we're taking a derivative with respect to x. So if I take a derivative of x with respect to x, that's 1. If I take a derivative of y with respect to x, that's y prime. So right here, derivative of x with respect to x, so I just put 2x. Derivative of y with respect to x, I'm going to put 2y, but then I'll put that y prime. Here, it's a constant, so that's 0. Now I'm going to go ahead and solve for this y prime. So this gives me 2y, y prime equals negative 2x. Y prime is negative 2x over 2y. The 2's go away. And just like we had before, y prime will equal the negative x over y. This is my slope equation. And where do I want the slope? I want the slope at an x value of 1 and a y value of negative 3. So this becomes negative 1 over negative root 3, right? Because this negative right here. Don't forget about that. Well, those go away. So the slope is 1 over root 3. Now I write my equation. Y minus y1, so that'll be y plus root 3, equals my slope times my x minus x1. And there is the slope of the tangent line of that. So let's take a look at example number 2. All right, this is one you guys, believe it or not, are familiar with. Whether you realize it or not right off the bat, I'm going to graph it to show you your familiarity with it. I think I could say that word. Okay, so when I graph this, we're going to go out 1, 2, 3, 1, 2, 3. Then we'll go up 1 here and 1 there, and it goes through here, it comes out, it goes over like this, it's a rose petal on that side, it comes out, goes over like this, it's a rose petal on that side. Guess what that is? It's the infinity symbol, and this is called a lemniscate. Let me spell that for you. Lemniscate. And I believe Jacob Bernoulli came up with that name for it. I don't know quite the details of it. I don't remember, but I think he's the mathematician that came up with the name for this infinity symbol. It's just based on another word, I believe, if I remember correctly. But anyway, let's get into the nitty-gritty. Here's what we got to do. We got to find a tangent at that point. Guess what? Try to solve for y. It ain't going to happen. Good luck trying to isolate y in this. Yeah, you're going to have to FOIL it out. Put everything on the same side. You'll have y's all over the place. It won't work. So we need to use differential equations. Again, let's recap. When do we use differential equations? When I can't solve for y. When I can't isolate y. If I'm trying to get an f of x, right? Y is my f of x. If I'm trying to get one variable in terms of another, and if I can't isolate that variable, then I need to use implicit differentiation. So that's what we're going to do here, and that means I need to take the derivative with respect to x of this whole thing right here, this beginning part, equals derivative with respect to x of the other side right there. I'm not going to write it all out, not just yet. For this example, I'm going to do it with a d over dx form, which will give me the dy over dx instead of the y prime. We'll do more y prime examples in a little bit. Okay, so over here, I'm going to take the derivative with respect to x of this whole left side. So that becomes 3 times, right, that's my constant, and I'm going to end up using a chain rule here, and this will be 2 times x squared plus y squared to the first power times, now I have to take the derivative of this inside part. So this will give me 2x, right, dx over dx, which I don't write, plus 2y dy over dx, just like that, equals. On the right side, it'll be 25 And now here, there is no chain rule or anything involved in this one. So this will just be 2x dx over dx, which I do not write, minus 2y dy over dx. You're always writing what you're taking the derivative of. It follows on, because that's technically part of the chain rule of it. So I don't write my dx over dx. I could write it right there, but I don't, because that's just 1. So there's no point. But I always have to write here because I took the derivative of y, but I took it with respect to x, so I need to include that. Okay, so now let's continue on. Over here, I'm going to take this 2 out, right? I'm going to factor the 2 out on both sides. So if I factor a 2 out over here and I factor a 2 out over there, those, believe it or not, will reduce out. So then I'm going to be left with 6x squared plus y squared, and then this will be, I took the 2 out, plus 2y dy dx. Right? I factored a 2 out of here, I factored a 2 out of there, and it canceled out of each side. I kind of saved myself a step there, so I don't have to write all that in detail for you. And now on this side, now on the right side, I'm just going to distribute, so I'll get 25x minus 25y dy dx. All right, let's see what I can clean up and distribute over here as well. So over here I will get, let's just say 6x squared plus 6y squared. And then I'll end up with x plus y dy dx. Over here I have this 25x minus 25y dy dx. Okay, now I'm going to FOIL the left side out. So I get 6x cubed plus 6x squared y dy dx plus 6xy squared plus 6y cubed dy dx equals 25 minus, or 25x minus 25y dy dx. All right, now on the left side, I'm going to combine like terms, which I don't think there are any, but I'm going to collect the dy dx's. So I will have 6x squared y dy dx plus this 6y cubed dy dx. I'm going to move this over to the other side, plus 25y dy dx, because I'm collecting all my dy dx's on one side of the equation, because I'm going to factor those out, because that's what I'm solving for. Equals. These two will go to the other side, right? So I'll move these over to the other side, and with this 25x. So on the right side, I will have negative 6x cubed minus 6x squared y minus the 25, plus the 25x. Okay, take out the dy dx that they have in common, and I'm left with 6x squared y plus 6y cubed plus 25y equals negative 6x cubed minus 6x squared y plus 25. Solve for this, so dy dx, and that's my slope, by the way, equals this 6x cubed minus 6x squared y plus 25x, sorry, there was an x there, all over this stuff that I'm dividing to the other side. 6x squared y, this stuff right here, plus 6y cubed plus 25y. And that's my slope. Guess what I got to do with that slope? I got to plug in the point right here, 2, 1. So plug this point in. And to save you the math and the space, I went ahead and then did that. So at 2, 1, I plug it in. I'll end up with negative 48 minus 12 plus 50 all over 24 plus 6 plus 25, and that becomes negative 2 over 11. That's my slope. Y minus y1 equals negative 2 over 11, x minus x1. This is the tangent line to this graph right here at 2, 1. So at 2, 1, right here, 2, 1. That is the tangent line. Okay, let's see what other examples we have. That was pretty crazy. That's kind of intense. Okay, here are some additional examples. We're going to find y prime. So let's go through and do that. And let's just pick another color here. Let's just go with another one. So over here, I'm going to choose the y prime notation. Up here, remember, I did the dy over dx. So over here, I will do the y prime notation, and we'll do the following. We will have this one, and I will have to use the product rule. So over here, I take the first times the derivative of the second, derivative of y is 1, times y prime, plus the second times the derivative of the first, which is 1, but I do not put x prime. Why don't I put x prime? Because that's dx over dx, which is just 1, equals the derivative constant right here is 0. So I end up with xy prime plus y equals 0. Over here, I solve for the y prime. I'll end up with xy prime equals negative y prime equals negative y over x. So I differentiated implicitly. But then you say, okay, Mr. N, hey, can't I have just done this one explicitly? Well, you sure could have. Watch, I'll show you. Look. If you chose to solve for y, now take y prime, right? This is x to the negative 1. You'll get negative 1, x to the negative 2, which y prime would be 1 over x squared. How is that the same answer? Well, what do I know that y is? Look, you told me y is 1, right here. You told me y is 1 over x. Y prime. Let's plug it in. Let's use the same color over here that I did. I don't know why this eraser is doing that, but okay. All right, so let's go ahead and do that. And we said y prime equals, well, let's substitute what this is. You told me y was 1 over x. 1 over x, right here. Over x. Guess what you get? Negative 1 over x squared. I forgot the negative right there. There is a negative. Sorry. So it's the same exact answer. Okay, but look at number 2. There is no way you can isolate that y to do this. There's just no way. So we will do it with implicit differentiation. All right, let me pick a different color here. I'm always stalling because I'm picking these colors. All right, over here, so let's take a look at this. So we have x squared minus xy plus y squared equals 0. We need to find y prime, and I'm going to do it with the y prime technique again instead of the dy dx. So starting here, taking the derivative of this, I get 2x, and I don't write the x prime, remember, because that's dx over dx, which is 1. Right? If I'm taking derivative of x with respect to x, I'll take that, and I'll put an x prime. Y with respect to x, I put a y prime. But we're not going to do the x primes, because they become 1. They reduce out. Minus. Over here, I need a product rule. First times the derivative of the second, which would be the derivative of y, and that would be just 1, but I need a y prime, plus the second times the derivative of the first, which is 1, and I don't write x prime, plus the derivative of this guy, which would be 2y y prime equals 0. The derivative of a constant is 0. The derivative of 0 is 0. So now let's distribute over here. 2x minus xy prime minus y plus 2y y prime equals 0. Collect the y primes on the same side. That would give me negative x y prime plus 2y y prime. And then I'm going to put all these on the other side. So that would give me negative 2x plus the y. And now solve for y prime by factoring it out. So I get negative x plus 2y equals negative 2x plus y. So y prime would be this negative 2x plus y, divide this over, divided by negative x plus 2y. Okay, often you guys will do steps a little bit differently than I do, and that's okay, that's fine. But then you will get like the opposite answer of what I got by like factoring out a negative, say. So like for example, if I factor out a negative on the top over here, I would end up with negative, and I'd have 2x minus y. If I factor out a negative on the bottom over here, I'd get a negative x minus 2y. So this answer would be 2x minus y over x minus 2y. Well, these are the same exact answers, right? It's just one has a negative factored out. And so it just ends up being the same thing, even though it may not appear to be right away. Okay, taking a look at the next one. Let's try this next one now as well. I've got 5y squared plus sine y equals x squared. Okay, so taking the derivative here, I'll get 10y prime plus the cosine of y prime equals 2x. I don't write x prime. Okay, factor out the y primes. You'll get 10y plus cosine y equals 2x. So y prime ends up being 2x over 10y plus your cosine y. And all done there. All right, moving on. Let's take a look at, we have our last example right here. And then we're going to do a few more examples in class, of course, as we always do. All right, let's take a look at what we got. Let me go to my color wheel and pick a color. And looking at this problem, it says find the tangent at 4, 0 to this equation. I did all the ones above with y prime. Let's go back to the other notation, the dy dx notation. Okay, so starting with this, finding a tangent means I need to find a slope. Finding a slope means I have to take the derivative. So that means over here, 4 times 7, 28, y to the third, dy dx. Plus, over here, I need a product rule. This will be first times derivative of the second. Derivative of y is just 1 dy dx plus the second y times the derivative of the first, which would be 3x squared. Dx over dx, but remember, I don't put dx over dx because it's 1. Plus, over here, the derivative of this is 1 dx over dx, but I don't do that, equals, and then derivative of 4 is 0. Derivative of a constant is 0. So cleaning this up and collecting all the dy dx's on the same side, which is pretty much these two terms, I'll get 28 y cubed dy dx plus x cubed dy dx equals, bring these over, this will be negative 3yx squared minus 1, and taking out a dy dx, I'll be left with 28y cubed plus x cubed equals negative 3 x x squared minus 1. Solving this for dy, oops, I don't know what happened there. Let's go back to this. Solving this for dy dx would yield negative 3yx squared minus 1 all over 28y cubed plus x cubed. Now, I need this at the point 4, 0. So I put in 4 for the x, 0 for the y. So I'll end up with negative 3 times y, which is 0, times 4 squared minus 1, all over 28, y, which is 0, cubed, plus x to the third, and that yields negative 1 over 64. And that is my slope. So now I can use that slope and finish writing the equation, and that would be y minus y1, which is 0, right? Then negative 1/64th, x minus x1. So that just yields y equals negative 1 over 64 times x minus 4. And there is the equation of my tangent line to this function. All right. Hopefully implicit differentiation wasn't too bad. It does take quite a bit of practice. And let me remind you guys something. Don't forget the derivative of a constant is 0. Often I see you guys keep this here, keep this number down here. Derivative of a constant is 0. So, thanks for watching. Hit that like and subscribe button, and I'll see you guys in the next video.